Konnichiwa. I am Jaewoong. I'm working at RevenueCat as a senior developer advocate and engineer. And I'm a Google developer expert for Android and Firebase. And I'm today going to talk about how to build robust Android libraries and SDKs from my experiences. Also, if your app is based on the multi-module architecture, you will get some useful tips. I've built on and maintained 100 open source projects under the nickname skydoves, and they are downloaded more than 20 million times every year, and run on more than 1.5 billion devices. Before we dive into building libraries, let's talk about the API surfaces. So what is an API? API stands for Application Programming Interfaces, which is a set of rules and protocols that allow different software systems to communicate with each other. And it doesn't only mean the RESTful APIs for fetching data from the network, but also it contains the libraries and SDKs we use in our daily life, such as Jetpack Build Model, Jetpack Compose, Firebase SDK, and RevenueCat SDK as well. So let's explore the API surfaces with a scenario. Imagine a library or SDK as a square, and there are public interfaces, which are illustrated a circle inside the box. Since these interfaces are public, any application depends on this library can access those interfaces. The problem is that if any of those public interfaces are broken, each application that depends on this library can be affected while updating to a new version, and they will face build failure. So library users should care about migrating to the new version, and library maintainers should consider every public interface. Now imagine only the orange ones are public, and everything else is for internal use inside the library. Since we've limited the public API to the orange ones, library users can access only these orange ones. So that even though the internal interfaces have been changed or broken, or expanded and reorganized for the internal structures, the library users will not be affected. So these limitations bring two benefits. First, library users don't need to investigate huge resources in migrating to the new version. And second, library maintainers don't need to worry about the entire interface surfaces. So it's easy to maintain the library and also can prevent the potential API misuse from the user side. For that reason, library developers really care about the visibility modifiers from the private to public based on the API specifications. In Kotlin, if you don't specify a visibility modifier, it will be public by default. So any application that depends on your library can access those classes, functions, and properties. And imagine you are building a library for providing a retrofit call adapter. And normally, the call adapter should not be accessed from the user side, since it will be created by the retrofit call adapter factory class. But if you don't specify any visibility modifiers, users can still access to the class, and then someone might misuse the APIs. Such classes don't need to be exposed to the outside, should be marked with internal or private visibility modifiers. So you can prevent the potential API misuse from the user side. And if you have any extension functions intended for internal use, it's much more important to add visibility modifiers. Extension functions are very convenient to add new features and functionalities to existing types without modification. But if you leave them public, they will be a part of your module's API and can appear anywhere. And it will be ended up with bad developer experiences. And likewise, you should add visibility modifiers to extension functions if they aren't designed for consumers. However, there's a problem. Even if you mark an extension function as internal, it can still be accessed from the Java side. The reason why is when you decompile an internal functions and extension functions, it will be turned into a public final static method in Java bytecode. So Java can still access it. For this, you can leverage JVM syntactic annotation. JVM syntactic is designed for Java interpolations, and if you add it to the internal functions, you will see the functions will be marked with the syntactic keywords in Java bytecode. And then those internal functions will not be accessed from the Java side anymore. And properties all the same. By default, Kotlin compiler automatically generates getters and setters for your properties. So you should also specify visibility modifiers to your properties or extensions as well. So now you must be wondering, is it really possible to manage the entire visibility modifiers for thousands, tens of thousands of your classes, methods, and properties in the whole project? You can manage them easily by enabling the explicit API mode, which is provided by the Kotlin compiler. Once you enable the explicit API mode in your Kotlin or Android project, it will validate if any classes, functions, and properties don't have explicit visibility modifiers, wall fields, and return types. As the example shows, if you don't specify visibility modifiers or explicit return types, you will face a compilation error. Once you've added them properly, now you can build your project without any message. And however, it's very challenging to add visibility modifiers for the whole project if you haven't enabled it from the scratch. In this case, you can enable the explicit API warning mode instead of the error mode. Then you will see compilation warning messages instead of errors. And you can gradually add visibility modifiers across a module by module and potentially the entire project. Once you've added them properly, now you can build your project without any message. And, so now let's go back to this API surfaces scenario. Even with a minimized public API surfaces, the changing the exposed APIs is inevitable during major updates. The thing we can provide better developer experiences is caring about the deprecated APIs in the API lifecycles. And let's say there's just a normal public function. If you remove the API in the next release, users will face a compilation error. And users should go to find any documentation or figure it out by themselves. It's pretty time-consuming and provides some bad developer experiences. A great solution for this is to use the deprecated annotation. If you add a deprecated annotation to functions that are supposed to be removed in the next release, users will see the kind migration message instead of facing a bad compilation error. Also, you can leverage the replay suite parameters to allow users to replace to new APIs, which is a great guideline. And once you feel users really need to migrate to new APIs, you can upgrade the deprecation level to error. Then users will see the kind migration message with the compilation error. While we can control the API deprecations in the API lifecycles across several versions, but sometimes we really eventually need to remove those APIs for better maintenance. The problem is, even though we provide the deprecated annotations for the migration guidelines, users can directly jump to the removed API versions, and they still face the build failure anyway. In this case, you can provide dedicated documentation about the deprecated APIs, which provides a great developer experience. So keep in mind that open source libraries and SDKs are a product for developers. So providing a great user manual is very important. So the key to API management is compatibility. then you must be wondering, how can we detect the public API changes since it's directly connected to compatibility? There are several types of compatibility depending on how we define it. But normally, binary compatibility is the strictest and the most important type. Binary compatibility means any apps using your library should compile well without recompilation. So, in a nutshell, by validating binary compatibility, we can detect if any publicly exposed signatures have been changed. Thankfully, there's binary compatibility validator plugin built by JetBrains. And you can easily validate and generate the current version of the binary compatibilities of your library. Once you run the API dump command line, you will see module.api file has been generated. And you will see the entire public signatures are contained. And then, whenever you change any public APIs, you can regenerate the binary compatibilities. And you can compare them to the old one to check which public APIs have been changed. So it's very useful when you review your new code changes, and it will prevent the potential changes of the public APIs by mistake. And there's another tool for checking binary compatibilities called MetaLava, which is built by Google. MetaLava is used by most of Google's Jetpack libraries and RevenueCat SDK as well. It works very similar to binary compatibility validator, such as excluding specific sources and naming outputs, files, and so on. And then, why does RevenueCat use MetaLava? Well, in functionalities, they don't have huge differences in most cases, but the binary compatibility validator doesn't respect the product flavors in the Android project. Since the plugin was initially designed for Kotlin projects. So you can consider using MetaLava if your library or SDK has product flavors. On the other hand, RevenueCat's KMP SDK uses binary compatibility validator since it doesn't contain any product flavors. And you can make it easy by leveraging Git hooks and CI pipelines. So you can validate binary compatibilities on your locale machine or CI machine, depending on your taste. And now let's talk about UIs in building libraries. If your library or SDK contains UI components or resources, there are some key points that you should keep in mind. Normally, if your library targets Android instead of pure JVM, the result file will be AAR file. AAR file is format used by only the Android platform to pack up everything about your Android library, such as classes and resources, kind of layouts, drawables, and strings, even the Android manifest file. So you can imagine most of Jetpack libraries and open source libraries and SDKs are delivered as an AAR file. And the Gradle system automatically downloads those AAR files for your project. And if you unpack an AAR file, you will see their entire resources around your library, such as classes, assets, and ProGuard. Especially if you look into the resources directory, you will notice that the all Android resource files, such as strings, colors, and styles, are bundled together. So these resources will be integrated into the library users project if they add a dependency of your library. In other words, the resources used in your library are very transitive. So let's imagine your library version 1.0 contains a set of colors with very general names, such as blue, white, and yellow. And the library user uses those resources in their project. And if you remove some of those colors in the next release of your library, the library users must be very confused because they will facing a resource not found error. And it's very difficult to debug where the resource comes from, especially it has a very common name, such as blue and white and yellow, brown. And if a user updated several libraries at the same time, it's very time-consuming to figure it out the exact reason. So there are two solutions to resolve it. The first one is the public tag. You can define resources that only should be exposed to the library users in the public.xml file using the public tag. For example, layouts, strings, colors, attributes, or Android relevant resources can be defined in the public file. And our other resources that are not defined in this file will be marked private. So let's see an example. If you don't specify any resources with the public tag, the library users can access and use all of them on their project with the IDE's auto-completion feature. But if you limit the exposed resources, Android Studio will not auto-complete the resources that are marked with private. It's not able to completely prevent access to the private resources if users just type manually those names, but at least they will see lint warnings. This warning is provided by Android Studio lint checking tools by default, so you don't need to configure anything else. And now let's see another example. Imagine your library contains an arrow image file under the drawable directory. And the library users can access and use the same resources because it comes from your library. However, if library users create exact same name of a resource like arrow, it will override the original resource from your library. This can completely break the expected behavior of your library or SDK. And users will complain that something has been broken suddenly, even though they haven't directly modified anything related to your library. To prevent this kind of issue, it's a great practice to set a clear naming convention for your library's resources. You can simply set the naming convention rule of your resources by adding the resource prefix on your Gradle file. Once you've set the prefix naming convention, you will see the compilation error if any kind of your resources doesn't follow the naming convention. Eventually, it forces your project to have the same prefix naming, and it will prevent your library users from overriding your library or SDK resources by mistake and breaking the features. And now let's talk about dependencies. Imagine your library depends on the material design component library, and the other Android projects use your library. It doesn't have any problems right now. But at some point, users also need to use APIs from the MDC library to call your functions. Then your library should propagate the dependency using the API function on Gradle. Then it's considered a transitive dependency. It will be propagated between packages, no matter how many are involved. And at the end, the endpoint project will compile and import the transitive dependency. In the worst case scenario, your library users might also import a very different version of MDC library, which could lead to conflicts if the versions are incompatible. For example, if you look at the JPEG fragment library, it contains a couple of transitive dependencies, such as view pager, activity, and lifecycle libraries. So if your library depends on the fragment library, it will unintentionally propagate a bunch of additional dependencies. As a result, developers who import your library might experience unexpected behavior changes across their entire project due to these propagated dependencies. The thing is, when you build your own library or SDK, it's very important to handle the transitive dependencies under your control. Also, you should minimize the transitive dependencies. And if you can't avoid it, keep observing them whenever you update to a new version. And now let's talk about the R class. Does anyone really remember the old school Eclipse IDE for building your Android apps? In the area of Eclipse or a very early version of Android Studio, we were able to access the R class. The R class is a resource class which maps our Android resources into static fields at compile time. So you can access the specific resources, and it's a very traditional system in Android development that we are still relying on JPEG Compose as well. Anyway, the R class is also very transitive. Imagine your library depends on the MDC library. Then in compile time, the MDC library will generate its dedicated R class. The thing we need to focus on is, in compile time, your library will generate not only your own R class, but also it will generate the R class for the MDC library as well. At the end, the M module will generate 3 different R classes about your app's R class, and your library's R class, and the MDC library's R class. So the R class for the MDC library will be generated at least 3 times in this scenario. And it's transitive dependency, even though we didn't contain the library using the API method on Gradle. So the secret is here. This library doesn't contain any sort of resources, but just contains the material library. And if you unpack the AR file, you will see it contains a ton of resources classes in your library. And if you just pick one and open one of the classes, you will see a huge lines of code related to the resources of material design components. Which means you're generating tens of thousands of lines of code in the R classes at compile time, since the entire resource definition will be generated at least 3 times. This is one of the main reasons we frequently face the multi-DEX issues. The DEX format has a 64K method and field limits, which includes everything from your app and its library dependencies. So transitive R classes contribute massively to this count, as they can be generated multiple times across different packages. So our king god, Jaewoong Onisama, pointed out this multi-DEX problem many years ago. And the thing is, multi-DEX limits count the fields resources as well, not only the method references. And those R class fields are replicated when pulling dependencies. So it's very easy to reach the 64K limits. And nowadays, you can easily disable the transitive R class problem by enabling the non-transitive R class option on your Gradle.properties file. But if you use AGP plugin over 8.0, it's enabled by default. And once you enable the non-transitive R class option, your library will no longer replicate the R classes from its dependencies. And as a result, the app module will generate its own dedicated R class. So before enabling the non-transitive R class, users can access our resources from the dependencies like material design library, and even if you don't import it directly. And if you enabling the non-transitive R class option, you will see you can only access the directly imported libraries resources. And resources from the material design library are not replicated anymore. So understanding non-transitive R class is pretty important. And not only when you're building your own libraries and SDKs, but also working with a multi-module architecture. Because each Andre module behaves very similar to single library. So once you enabled the non-transitive R class on your module, you might encounter the resource not found issue, since the endpoints, such as the app module, will not generate other packages, R classes, fields anymore. To access resources from other libraries, you need to use their full package names or simply access by importing them using namespacing. So today we've touched on various topics to make great libraries and SDKs. First, minimizing API surfaces is important for both library users and maintainers. And second, managing API lifecycles and caring for API compatibilities lead to great developer experiences. And third, minimizing exposed resources is very important if your library contains UI components and resources. And lastly, transitive dependencies also need to be considered and enable the non-transitive R class as much as possible. So I really hope today's talk was helpful to build your own open source libraries or SDKs, or if you work at the modularization team. And you can also check out the slides on the QR code below. And I will be in the RevenueCat booth. So if you have any questions, just come to me and ask anything. So thank you so much for your time today, and enjoy the rest of the sessions at DroidKaigi. ありがとうございます。